Hi, everybody. Welcome to the video series for representing solute transport processes in the BioRT-HBV model. I'm Liz Andrews, and I'm going to start the first video with some solute transport background and theory. So what is solute transport? It's the non-reactive transport of solute in a fluid. Three main processes contribute to solute transport, including advection, diffusion, and dispersion. And we're going to walk through each of these a bit more. So let's start with advection. Advection is the movement of solute at the same velocity as the fluid. And so we have this box that sort of represents a fluid and an arrow that represents the flow velocity. And we have our red solute. And so it's just going to move at the same velocity through the system as the fluid does. And so this box could represent a pore, it could represent a column, all kinds of things. It could represent the start of a watershed. But advection will just move the fluid through the system at the same, it will move the solute through the system at the same rate as the fluid moves through the system. Now let's move to diffusion. Diffusion is the movement of molecules in response to a concentration gradient. So now in our space, we have our solute and it's concentrated in one area, that one red circle, and there's no solute anywhere else. And so what's going to happen is the molecules are going to move apart to smooth out the concentration gradient so that there eventually is no concentration gradient, that the same concentration exists everywhere. Now, this is in a very simple, just water type case. It gets a bit more complicated in the porous media that we might be representing in a watershed, where we have soils that have solid particles along with just the fluid. And so the path for the diffusion can be longer because the molecules of concentration or solute have to take tortuous paths or just longer paths around the different particles to spread out. Now, dispersion is the last process, and it basically is the mixing of the solute as a result of fluid velocity fluctuations around the average fluid velocity. So this could represent basically if you had a single pore or say a column with sides, you have an area where along the edges of the system, there's no flow along the boundaries. And then we have the fastest velocity in the center of the system. And so that leads to mixing along that, where we have the spreading of the solute because of that fluid velocity difference between the space in the pore or in the column or whatever system we're working in. It can also be the result of mixing of many flow paths. And that's going to be really important for us with the BioRT-HBV model, because we distinctly represent three flow paths, which each have different lengths, and then that will contribute to this dispersion in the system. If we try to describe this with an equation, we have the advection dispersion equation, and this is just an overview of it. If you want more details about how we get to this equation, I recommend you visit the website at the bottom of the page. But what this equation says is that the change in concentration with time is equal to the advective flux, or the solute that moves through due to advection, and the hydrodynamic dispersion. And that is basically a combination of both diffusion and dispersion. And those two processes combine to make the advection dispersion equation that goes into simulating solute transport. We have no reaction here. This is just non-reactive transport through a system. The way that we look at this and describe the system is with a breakthrough curve. And so here's a simple conceptual breakthrough curve where we have tracer concentration on the y-axis, and we either have distance or time on the x-axis. And so it depends how you're representing things. If you're representing, say, movement of tracer through a column, this would be distance. But here we're going to be looking at the movement of tracer out in the stream And so it's more like we're looking at one point in space, and we're looking at the concentration moving through with time. And if we have only advection, we have this dotted line here, and you can see that it is relatively non-dispersed. We have a sharp peak, and then if we add dispersion in, we get a much softer peak. It's spread out more in either space or time and has lower concentrations. And so, like I said, in BioRT, we have many different flow paths, and we would expect that we might see something that looks more like the advection and dispersion combination if we look at our breakthrough curves. So, quick overview of what the BioRT-HBV model structure looks like. This is a conceptual model on the left of a watershed or a hill slope that we're trying to represent. We have surface runoff, and then we have a shallow soil zone, and then we have a deep zone, and we have flow out of each of these different zones. So we can have surface flow. If we look at the center part of the panel, we have our inputs and our outputs in each of these boxes. So HBV BioRT is a bucket type model that represents the three zones as different buckets with inputs and outputs. So we have precipitation and evapotranspiration balancing with discharge out of the system as the water balance. And they both are inputs. Precipitation and evapotranspiration are inputs to the surface, or outputs in the case of evapotranspiration. We have infiltration, some infiltration through the surface and some runoff. And we have chemistry of the surface runoff along with the discharge of the surface runoff. Then what infiltrates into the shallow zone, we have, again, a movement of the solute and the fluid out through the shallow zone, and that can contribute to the stream. And then we also have some movement from that shallow zone into the deep zone. And from the deep zone, we also have fluid that leaves the system with a certain chemistry. And altogether, we do a flux weighted average to look at how much discharge comes from each of those zones and what the chemistry is to determine the stream chemistry and discharge. So what we're going to be looking at when we look at the results of these simulations is typically the stream chemistry and the stream discharge. And that will allow us to construct a type of breakthrough curve like we just saw. And then we can say what's happening in the system based on whatever conditions we're testing. And so this is just a brief overview of solute transport and in the background and theory and how it might apply in BioRT-HBV. The next module that you'll see is how to set up an example of solute transport in BioRT-HBV model. Thanks for tuning in to the first video, and be sure to tune into the second.